Alright, this is my second case for Project 3. This is going to be the Viscous Laminar case. So I already got the mesh and geometry set up. Like I said, it's the same as in the Inviscid case, if you want to go back and watch that one again. But I'll go right into setup. Double precision, 4 solver processes. Okay, now here we are in the setup. First thing we're going to do is switch our model to laminar. Hit OK, and then we're going to go to results, residuals, and turn these down to 10 to the negative 6. Alright. Materials, fluid, air. I'm going to adjust some of the properties of air. I'm going to make the density 1 and the viscosity 1 times negative 10 to the negative 4. And I'm going to go to boundary conditions, inlet, and adjust the velocity to 0.01. If you do the math on this, this will give you a Reynolds number of 100. So very low Reynolds number. This should absolutely be laminar flow, and there should be no issues there. Okay, now we're going to go to the bottom and top because they're by default walls, and we're going to make them symmetries. Boundary conditions. No, not info. Type symmetry. Okay, this wall should be no slip. Let's make sure it is. Stationary wall, no slip, great. And now we're going to go to our reference values, and we are going to compute these from the inlet. Now we're going to leave the methods unchanged for viscous laminar flow. Before I changed the scheme to simple and the pressure to presto, but this time we're just going to leave them on the default, and we're just going to go straight to initialization, double click into this, change this to 25 iterations, and initialize. Okay, the initialization just finished. We can now run our calculation. We're going to do 300 iterations and calculate. Okay, our calculation is now complete. Here are our residuals. Pretty steady decline, much better than the Inviscid case was. But from here, we can go to plots, XY plot, new, and we're just going to plot the pressure coefficient as a function of x on the cylinder body. Let's plot that, and here we go. Okay, so it's a bit strange. It starts out about 1, and then it dips negative, and then it's supposed to rebound fully. It doesn't quite rebound fully here. It kind of just tapers off a little bit, and it comes up a tad bit, but it's supposed to come up a little more than this. But I mean, everything else looks pretty much okay. If we go to reports, forces, let's just print these, and I'll show the velocity and pressure contours when we get to the results section. But here are our drag coefficients. We've got about 0.79 for pressure and about 0.28 for viscous. So viscous is pretty, you can't neglect viscous with laminar flow right here. And the total is about 1, drag coefficient of 1. Okay, and now onto results. Alright, now let's see what's going on here. So let's get a velocity contour in, and we will use 301 contours on the symmetry 1 and hit apply. Okay, so here's our velocity contour. So you can see once again stagnation point at the front. That's going to be pretty much the same in all of these, and then it very quickly departs. It seems the streamlines get bumped off at around this point, and they don't trail along the cylinder for very long, which creates a pretty wide wake region, which is what we're looking for. And there is some weirdness that happens here, and that's probably because if you look, this is like kind of a circular shape. Probably has to do with the fact that we used an inflation mesh here, and then it suddenly transitioned to the triangular mesh, and that probably had something to do with it. I'm guessing this is just an artifact of the transition from one mesh type to another, though I'm not quite sure. But either way, the shape is pretty much exactly what I was looking for. It's a pretty sizable wake region, and it's quite long, and eventually it trails off and becomes pretty normal velocity again. Alright, next let's get some streamlines in here. And we'll do start from the inlet, 1,000 points. Alright, and here are our streamlines. So, of course, they diverge right here. There are no streamlines that hit this point. And they separate for quite a long time. Once again, this is a very wide wake region. Very little, very few streamlines could reach here. Even if you picked ones smack dab in the middle here, they would have a hard time getting to this point. But eventually they do reconverge, and by this point it's pretty much going to be normal flow very soon. So last thing we need is a pressure contour. And we'll do 501 contours, and location symmetry 1, apply. Alright, here we go. Pressure contour is done. So let's take a look at what's going on. Okay, so very high pressure here as expected, and then low pressure here. Low pressure wake region as well. So you can see the lowest pressure is right here where the velocity is the highest, and the streamlines break off from the cylinder just before the halfway point, and then it starts to normalize, which is what we want. Now, while in the in the pressure coefficient graph that we looked at earlier, it doesn't rebound quite as much as it should. It does rebound a little bit, and that's very clear here. The lowest pressure is right before the peak on the cylinder, which is exactly what we want. And then the rest, it slowly rebounds. Alright, that's it for the laminar flow. I will be doing turbulent next.